In this video, we're going to review the idea of a linear span. So here's a definition. Let's let V be a vector space over F, which is a field. And let's let S be a set of vectors in V. All right, we define the linear span, or usually just the span of S, and it's usually written span of S, to be the following set. The span of S is equal to the set of all V in the vector space V such that there exists W1 through WK vectors in the set S and scalars alpha 1 through alpha k in F such that, sorry, this is like the longest set definition ever, such that V is equal to alpha 1 W1, etc. up through alpha k WK. End of set definition. Where should I put the closing brace? I'm going to put it over here and make it really big. And then make this really big too. Awesome. Totally elegant. Okay, so anyway, the span of S is the set of all vectors in V that can basically be written as a finite linear combination of vectors in S. That's the idea. All right, so so the span of S is the set of all finite linear combinations, or we could say F linear, if you wanted to clarify that the scalars have to come from F linear combinations of vectors in S. And here's a special case, and this is the case that actually we'll be working in most of the time in this course. If S is just a finite set of vectors to begin with, W1 through Wn, then the span of that is just the set of all linear combinations of those in vectors. So I can just write a little more simply, and I'll explain the distinction in just a second. There we go. So that makes for a little bit more compact definition. So the reason that the first one has to be so, I don't know, just so laborious, is that S may be an infinite set. We're not allowing infinite linear combinations. A linear combination, by definition, at least in this course, and in the linear algebra that we do, a linear combination has to be a combination of finitely many vectors from this set with corresponding scalars. So here, because I have an infinite set potentially, I can't commit to a specific fixed set of vectors that I'm using like I am doing here. So I'm saying it's the set of all V in the vector space such that there are vectors somewhere in S which could vary from V to another V, and corresponding scalars such that V can be written as a combination of those particular vectors. But like I said, most of the time we will be dealing with finite spanning sets because we'll be in finite dimensional linear spaces or vector spaces. So usually we can use this simplified definition here. Okay, couple of facts. Number one, the span of S is a subspace of V. In other words, it's a subset of V and a vector space in its own right. Okay, well, how do we know it's a vector space? Well, it has the same operation of addition as V has. It has the same operation of scalar multiplication. So really the main things to check when we're trying to show that something is a subspace, we need to show it's closed under addition and closed under scalar multiplication. And I'll say a bit about how to verify that in the case where S is finite. The proof for the general case is a little bit more complicated, but not a ton more complicated. It's just like a little bit more complicated. But if I'm in this case, then any two vectors in the span of S are going to be expressible as potentially different linear combinations of W1 through Wn. So by different, I mean the scalars might be different. But if you add those up, then you can combine the W1s together, combine the W2s, etc., and combine the Wn's, and just those scalars are going to add, and you have another element of the span of S. So you're closed under addition, and showing closure under scalar multiplication is not a lot worse because, again, any vector in the set or in the span of S is going to look like this. And then multiplying that by another scalar alpha just gives you a new linear combination of W1 through Wn with new scalars. So like if that scalar you're multiplying is alpha, then the new scalars are alpha, alpha 1, alpha, alpha 2, etc. up through alpha, alpha n. This is the worst dubstep track ever. Anyway, so span of S is a subspace of V. But equally important to know is the fact that span of S is the smallest subspace of V containing all the vectors in S. So containing S as a subset. It is the smallest subspace of V that contains all the vectors in S. Okay, why is that true? So you can actually prove this using a similar technique to how we proved that the principal ideal of A is the smallest ideal of a ring that contains A. And that is, we suppose we have some other subspace containing all the vectors here, and we show that that subspace is going to have to contain all of these, or I guess in the general case, all of these. All right, so, well, how do you do that? Well, if I have a subspace, let's call it W, that contains S, so it contains W1, W2, up through Wn, then what does that mean? Well, if it's a subspace, then it has to contain any scalar multiple of any of those vectors. So it's got to contain alpha 1, W1, it will have to contain alpha 2, W2, so on and so on. It will have to contain alpha n, Wn. And because a subspace is closed under addition, it has to contain the sum of all of those. So that's why I have to have all of these. So then once I have all of these, the span of S is a subspace of my supposed subspace W, which means this has to be the smallest that contains S. Okay, so those are a couple of facts. Now here's an example from field theory. I want to go back to the example of C, the complex field, as an extension field, but also a vector space over R. Okay, so what do we know? We know that C consists of all numbers that can be written in the form A plus BI, such that A and B are real numbers. So what if I ask, what is the span of this set? The span of 1 and I. Okay, well that's going to be the set of all elements of the form, let's call them alpha 1 times 1 plus alpha 2 times I, where alpha 1 and alpha 2 come from the scalar field, which is R. Okay, but what is that really? That's really just the set of all alpha 1 plus alpha 2I, where alpha 1 and alpha 2 are real numbers. And that's really the same thing as the set I just wrote down over here. I just renamed the scalars as alpha 1 and alpha 2. So the span of 1 and I is really just the entire vector space. It's all of C. So one way that we say this is that C is spanned by the set 1I. And it could also be spanned by other sets too. It's spanned by, and this is kind of a silly example, but you could say 2 and 1 plus I. That would be a perfectly good spanning set. It's less obvious that it spans C, but if you think about all of the complex numbers you could get by adding a real multiple of 2 and a real multiple of 1 plus I, well, this here is going to let you get any multiple of I that you want. So you can get any coefficient on the imaginary part that you like, and then you're also going to have a real part attached to it, and it may not be the real part that you want, but you can adjust that by adding or subtracting the appropriate real multiple of 2. So that's a little meta argument that this set will also span the complex numbers. So there's a lot of spanning sets. There's not a unique one. There's not even a unique smallest one because both of these are the smallest possible. You can span C with a set of 2 vectors, but not with a set of 1 vector. I'll leave that as an exercise to figure out how to prove why. But anyway, that's one example of how we use spanning sets in field theory. We'll see a little bit more about that when we start talking about field extensions in more of an abstract sense, where we don't have as clear of an idea of what the elements look like.